Okay, so today we're going to learn how to read solubility curve, which is a type of graph. So every graph has certain parts that it has to have in order to be a proper graph. So first we have to have a title. The title of this graph is solubility curves. Next, we need to have a label on the x-axis with units. So the x-axis has the title of temperature in degrees Celsius. That is our independent axis. That means that we are going to heat the solution up and then we're going to check how the y or dependent axis responds. So on our y-axis, we have grams of solute / 100 grams H2O. So that's going to change with changing temperature. So let's review real quick what that means, because that grams of solute in 100 grams of water can be confusing. So we're going to have, let's just say we have a beaker and we're going to have in there water. Water is going to be our solvent and it's going to dissolve the solute. So we're going to fill it up with 100 grams of water. Let's remind ourselves that the density of water is 1 gram per milliliter. That means if you have 1 milliliter of water, its mass will be 1 gram. So if I have 100 milliliters of water, its mass would be 100 grams, and that's what we're dealing. So we're basically talking about how much can I dissolve in 100 grams or 100 milliliters of water. So water is the solvent. The solutes are all of these substances that the lines are labeled with. So I'm going to dissolve them, and when I dissolve them, the particles will be in solution and will be the solute. So the solvent is water, 100 grams of water. The solute are the substances that the lines are corresponding to, and the solution is the solute and the solvent added together. Now let's go over and let's picture dissolving these salts in my beaker full of water. Notice that when I say salt, I'm referring to substances whose temperature increase results in an increased amount dissolved. Can anybody find a substance that decreases solubility? SO2, sulfur dioxide. Anybody else? NH3, which is ammonia. HCl. HCl, NH3, and SO2 all decrease in solubility with increasing temperature. Now let's look and see, can anybody tell me what those 3 substances have in common and they're different than the other substances? So all of the ionic compounds are my salts that increase in increasing temperature that increases the solubility. All of the other ones, the covalent compounds, are actually small covalent compounds, so they're gases at room temperature. So what you can interpret from here is that the solubility of gases decreases as temperature increases. Ionic compounds, the solubility increases as increasing temperature. That's because ionic compounds are always solids at room temperature, and the solubility of a solid increases with increasing temperature. You can even think of some larger, very large covalent compounds that are solids also, like sugar. You know that sugar is going to dissolve better in hot tea than it does in iced tea. So that also goes for even covalent solids. But the important distinction is that those small covalent compounds are actually gases. This is one of the reasons why climate change is becoming such an issue, because as temperature of oceans, lakes, rivers, and such increases, the solubility of dissolved gases decreases. That may not seem like a big deal to you, but you do know that fish are under there, and we all know what fish breathe, don't we? It's oxygen. So the dissolved gases decreasing with increased temperature means that there's less oxygen in the water. for them to breathe. You all know that when plants grow, they actually release oxygen. So when they do photosynthesis, it provides us oxygen. So this is all an important topic. So let's read what we can look. We can look on here and we can see Ki all the way over here has the greatest solubility. That line is considered its solubility. If you have exactly the right amount on that line, that is called a saturated solution. So saturated means that it's holding just as much as it can hold, and that's that particular solution's solubility. I can also look at Ki and say, I can interpret things that are not necessarily on the graph by what's called extrapolating. So standardized testing is notorious for this, is to ask you something that's not on the graph. You wouldn't say, oh, it's not on the graph, so I can't tell anything about it. What you would say is, if they said how much Ki, or potassium iodide, would dissolve in at 50 degrees Celsius in 100 milliliters of water, you would say, well, that's not on the graph, but I know it's going to be greater than 150 grams. So you can interpret things that are not necessarily exactly on the graph. So let's pick another one that's important on here. KNO3 right here. Notice how that line has the largest slope, meaning that it changes the fastest with increasing temperature. What that means is that KNO3 has the largest change in solubility as it relates to temperature. Can anybody find the smallest change in solubility? Devin? NaCl. That means that its solubility does not change very much with increasing temperature. Let's now summarize the fact that the largest solubility would be the one that dissolves the most. The greatest change in solubility would be the one that has the greatest slope. The smallest change in solubility would be the one that has the smallest slope. Ionic salts are increasing with increasing temperature. They increase their solubility. Covalent, small covalent compounds decrease, or gases decrease in solubility with increasing temperature. And we also learned that this line, or the solubility, would give us a saturated solution. Now, I'm going to take a different one. Let's go to NH4Cl. NH4Cl is an ionic compound because NH4 is a positive polyatomic cation acting as a group to form an ion. So on this line is saturated. Now, there's also a possibility that you have less than the amount that you could possibly dissolve. So anything under this line, anything less than a saturated solution down here, is called unsaturated. There's also something else I can do. I can take a saturated solution. Let's say my solution's at 90 degrees Celsius, and I have 70 grams dissolved in it. If I cool that solution down, I will have more dissolved in there. As long as I don't touch it and I let it cool, it'll stay dissolved. When you have more dissolved in there than the saturated level, you have what's called a supersaturated solution. So when you have a saturated solution and you cool the temperature down and you have more dissolved in there than should be possible, this is called a supersaturated solution. So supersaturated means I had a saturated solution and I cooled it down. And that means that more than possible is dissolved in there. What will happen, I can't even touch that solution, because if I even touch it with my finger or drop one more crystal of solid in there, what will happen is a lot of solid will fall out of solution as a precipitate. So precipitate is solid salt that falls out of solution because somebody disturbed a supersaturated solution. Now, a supersaturated solution is really important in like baking. So cooking and baking are two different things. Both involve a lot of science. But baking, you have to be super careful and super exact with your measurements. And supersaturated solution would be how we make things like fudge. And that's why it's so difficult to make fudge or make it well, is because you have to have a supersaturated solution. So let's talk about the fact that this is how much solid would dissolve in 100 grams or 100 milliliters of water. I want to point out that 1 milliliter, let's remind ourselves from earlier, is the same as 1 cubic centimeter or centimeter cubed. You might also see this written as cc's. We might have heard, oh, give them 5 cc's of fluid. Cc's is stands for cubic centimeter. That's also the same as a milliliter. That's kind of a nursing term. So if you're going in to be a nurse or a doctor, you're going to see cc's a lot, and it's the same as a milliliter. But what if my problem tells me that I don't have 100 milliliters of water? That's another thing that we can solve with this graph. So let's just take KNO3. Let's say I have a saturated solution. Remember, on the line is saturated. I have a solution, a saturated solution at 60 degrees Celsius. So at 60 degrees Celsius, this is how we write the solubility. I can dissolve 110 grams of KNO3 will dissolve in 100 grams of water. This is how we write the solubility. But what if the problem said I didn't have 100 grams of water, I only have 50 grams of water? Then you can set up what's called a proportion. So if 110 grams of KNO3 dissolves in 100 grams of water, then I need to calculate or solve for the number of grams, or X, because I don't know it, in 50 grams of H2O, or whatever amount your problem says you have. Well, I now can rearrange this equation by multiplying each side by 50. That will give me that X is equal to 50 times 110 divided by 100. So 55 would be my answer. So 55 grams of KNO3 dissolves in 50 grams of water. Like such. So you can do problems and even solve for values that aren't 100 either from this particular chart. So you can also say things like, I have 90 grams of KNO3 dissolved in 100 grams of water. At what temperature will a precipitate form? Well, when you cool it down, you're going to cross over the unsaturated, and once it hits the saturated, the rest will start to precipitate out. So you can say that at about 52 degrees Celsius, a precipitate will start to form. So there's a summary of how to read the solubility curve. And pay close attention to this, because this type of graph, of course, not only will be on the test, but you're going to see it on standardized testing all the time.